Okay, hello everybody, and first of all I would like to thank the organizers of this workshop and especially to Irina Sviridova for kind invitation to give a talk here. And the title of my talk is the Verão conjecture for finite dimensional algebras and its analog for pseudocompact algebras. It is based on the joint work in progress with John McCrory. And the plan of my talk is the following one. So actually, first of all, I will recall two important homological invariants for algebras. It is global dimension and also Hochschild homology. And then I will state Hence conjecture, which relates these two homological invariants in between. And then I will give introduction to recent results about extensions of algebras and also Jacobi-Zariski sequences, which helps to study these conjectures in a very specific case of actually extensions of two algebras, A and B. And then starting from 4 and 5, we will try to do something similar for the world of the pseudocompact algebras. And this is why I will do some very brief introduction to the pseudocompact algebras and also its modules. And also I will state some possible version of the Hence conjecture here. And finally I will present some recent results about this conjecture for the world of the pseudocompact algebras. Okay, in my talk, K always stands for the field, some fixed field, and A is always K algebra, which is in the first part of this talk is going to be almost always finite dimension. The global dimension of A, it measures how far is algebra A from being semi-simple algebra. And we can define this global dimension as follows. So, given any A model M, we can look at what is called projective resolution of M. Okay, what is this? And actually, there is some exact sequence which actually ends at M, and that has all of the other guys are projective raised models. And somehow, from some point of view, the projective models in this category A mod are the most simple objects because they are direct sums of the free objects. Okay, and actually to now global dimension of A, it is supremum of the minimum length of start of such projective resolution over all A models. Okay, and actually to now let us do some example. And example A is probably the most simple one. It is semi-simple cases. So, and actually let us suppose A equals to K, or A equals to Mn of K, or could be more like general semi-simple algebras. And in this case, any A model is already projective. And in this case, we can choose somehow the minimum projective resolution of the following form. So it's going to be 0 and 0. And hence it follows that the global dimension of A is going to be 0 here. And somehow more generally, for somehow any semi-simple algebra, global dimension of A, it is 0. And also vice versa. If you have algebra such that the global dimension is 0, it is necessary should be semi-simple algebra. Okay, and somehow to now a little bit more complicated class of algebra. It's going to be hereditary algebras, and algebra A is called hereditary if any submodel of a projective model is projective. So in this case, given any A model M, actually we can take a projective cover of M. Yeah, it's going to be projective cover of M. And actually to take in kernel of this map, it's going to be submodel here, and hence it's going to be projectable. And hence minimal resolution of M by projective models, it has length at most 1. And actually this is why global dimension of A in this case is less than or equal than 1. Okay, and actually let me say a little bit more words about hereditary algebras, and there is a canonical source for hereditary algebras. You can take a finite oriented graph Q equals Q naught Q1, and actually sometimes such graphs are called quiver. And it is something like actually the oriented graph, which somehow it has finite number of the vertices and also finite number of arrows, something like this. And actually let us take KQ, is going to be path algebra of this quiver Q. So actually path algebra, its basis are oriented paths in Q, and also multiplication is given on the basis by the concatenations of the paths when it is possible. Okay, and actually to this algebra KQ, it is finite dimensional if and only if it has no oriented cycles. And also we have the following celebrating theorem, which is due to Gabriel. If the field is algebraically closed, then any hereditary algebra A is Morita equivalent to path algebra of Q of A, where Q of A, it is Gabriel quiver of A. So actually to given hereditary algebra, you can construct some quiver Q, and actually to this quiver is such that when you will be constructing a path algebra of this quiver, it is going to be Morita equivalent to your original algebra. Okay, and somehow to let me introduce now a few more examples on the global dimension. So first of all, let us take the following algebra. A equals k of x over x squared, algebra of dual numbers. The dimension of this algebra, as it is very easy to see, it is 2. And if we will look at the A model K, and then somehow to the best possible trajectory resolution of this model, and it is given as follows. All the projective models are A, and all the maps are given by the multiplication by x here. And this is the best possible trajectory resolution, and it is infinite. And actually, what means that the global dimension of A is going to be infinite in this case. Okay, we saw algebras which have global dimension 0, global dimension 1, and global dimension infinite. And in fact, any positive integer, it could appear as a global dimension of some finite dimensional algebras. And actually to see that, and actually let me introduce you to the very simple examples. So actually this is the first example here, it is given by the path algebras. So actually let us take this following quiver which has n plus 1 vertices. And if we will look at the path algebra of this quiver, modular radical square of this algebra, the global dimension of this algebra somehow to this quotient algebra, it's going to be exactly n. And also one more example, and now let us take as a finite poset which has n plus 1 levels here, and the global dimension of the incidence algebra of this poset is going to be exactly n as well. Basically, any positive integer, it could appear as a global dimension of some finite dimensional algebra. Okay, and actually now let me briefly introduce the Hochschild homology, which were defined by the Hochschild in actually 46. It is just a family of K models, Hn of A, where A is again a finite dimensional algebra. Also, you can define it more general, Hn of A, comma M, where M it is just A by model, which are homology of second chain complex associated with algebra A. And in particular, just zero-degree homology, they have explicit description. So actually, H0 of A, it's going to be a Bellization of algebra A. It's going to be A over commutator AA. And somehow to later on, in somehow to 56, Cartan and Eilenberg, they give a functorial definition of Hochschild homology. And actually it turned out that the nth homology, Hn of A, it's going to be nth star functor over enveloping algebra An of AA. In which enveloping algebra AE is going to be a tangent product between two algebras, A and A opposite. And actually let me show to what is happening for the various the same examples which we looked at the global dimension. It is obvious that actually H0 of K is going to be K because K is already a commutative algebra. And also Hn of full matrix algebra MD of K, it's going to be K in the case n equals 0, and it's going to be 0 otherwise. And somehow to more generally, Hn of the direct sum of full matrix algebras, it's going to be just actually K into the power m when n equals 0, and it's going to be 0 otherwise. Okay, and actually now let us look at the case of some hereditary algebras. And first of all, let us fix the quiver which has m vertices, actually this quiver. And actually, if we will look at the path algebra of this quiver, it's going to be nothing else as the algebra of m by m upper triangular matrices over K. In this case, Hochschild homology Hn is going to be equal K into the power m, in the case n equals 0, and also 0 otherwise. Okay, and actually the more general, is somehow the Hochschild homology of the path algebra of the form KQ, where Q is some finite quiver. It is equal to K into the power Q naught, in which Q naught it is a set of vertices in quiver Q. In the case n equals 0, and also it equals 0 otherwise. And I have to remember that actually we are supposing that the quiver Q has not oriented cycles, because otherwise the path algebra will be infinite dimensional. In this case, it is also possible to compute Hochschild homologies, but the formulas will be much complicated. Okay, one more example. It was algebra of dual numbers. And in this case, somehow the zero degree homology is going to be the whole algebra, because this algebra is a commutative algebra, and hence abelization going to be the whole algebra. And also for any n not equal 0, we have the Hochschild homology, and it's going to be k in this case. And also one more example, in the case when we have a finite poset of actually this sort, or from somehow any other poset, and if we are taking the incidence algebra of this poset, in this case, zero degree homology, it's going to be k into the power s, where s is just number of the elements in this poset s. In the case n equals 0, and it's going to be 0 otherwise. So, and actually now let me give you a summary of what we solved by now. So, and it's going to be a table of the algebra we solved. And actually, somehow this column, it's going to be Hochschild homology, and in this column, it's going to be global dimension of algebra A. So actually, first I solved semi-simple algebras, and actually homology were concentrated at degree 0, and the global dimension equals 0. Okay, hereditary algebras, something of the sort KQ. In actually this case, again, homology concentrated at degree 0, and also global dimension of A equals 1. Okay, also we solve the somehow incidence algebra of actually such posets. In this case, again, homology is concentrated at degree 0, and also global dimension of such algebras equals n. And finally, we solve the case of algebra of dual numbers. In this case, actually homology can be for somehow any arbitrary degree, and also global dimension of this algebra is infinite. And somehow already these few examples gives a certain evidence for the following Hence conjecture, which relates Hochschild homology and also global dimension of algebra A. I will formulate it right now. Okay, actually we saw several examples, and actually we already saw a certain evidence to the following conjecture which is due to the Hahn, and which was formulated in actually 2006. So actually let A be a finite dimensional algebra, then the following two conditions are equivalent. First one, Hochschild homology of A vanishes for large enough degrees n, and second one, global dimension of A is finite. So actually the second condition almost obviously implies the first condition, because if global dimension of A is finite, then the global dimension of its enveloping algebra AE is finite too, and hence we can find a finite projective resolution of A as AA by model, And hence Hn of A, which is equal to a vector over enveloping algebra AE and AA, then it is going to be 0 for somehow all the degrees n greater than r. And also we have a more subtle result, which is actually due to color, and it claims the following: if the global dimension of A is finite, then in this case, Hochschild homology, it is concentrated at degree 0. Implication 1 implies 2 is somehow a way more complicated, but still it holds true for the following special classes of algebras. So actually it holds true for all the commutative finite dimension algebras, and actually this follows by the old papers which is due to Verão and also Jacobi-Zariski. It also holds true for all the monomial algebras, which was proved by Han at the same paper. And actually, what is monomial algebra? Monomial algebra it is just path algebra of some quiver modulo some ideal in which I is just generated by pure paths in G. It also holds true for all the causal, local and trivial extension algebras, and this is due to Berg, Madsen and also Ekman. And also there are many other cases in which this conjecture holds true too. And actually the lattice H, it will be the class of algebras which verify Han's conjecture. Recently, Claude Siebels, Eduardo Marcos, Marcelo Lancelota and also Andrea Solotar in the series of papers, they somehow were studying under which conditions on the extensions of algebras. So actually we have algebra A and also subalgebra B. And actually extensions of algebras show that B belongs to the class H if and only if A belongs to the class H. So, and in this context, it is naturally appear the following question: how to relate Hochschild homology of algebra B with Hochschild homology of algebra A? In 2012, Kaibun obtained a long exact sequence called Jacobi-Zariski sequence, which relates Hochschild homology of A, Hochschild homology of B, and also what is called relative Hochschild homology under condition such that A over B is projective as B bimodal. Actually, relative Hochschild homology is a homology of certain chain complex which you construct in terms of A over B, and also using relative BE projective models. Okay, Siebels, Marcos, Lancelota and Solotar, they extended the existence of such sequences for so-called bounded extensions of algebras. An extension BA is called bounded if we have the three following conditions are satisfied. So the first one, A over B should be left or right projective as B model. A over B is B tensor nilpotent, that's it. A over B tensor product that is B bimodal to the sum power n is going to be 0 for some n. And also projective dimension A over B as B bimodal, it should be finite. And now the principal result, which was obtained in the series of papers by Claude Siebels, Eduardo Marcos, Marcelo Lancelota and Andrea Solotar, is the following one. Let BA be bounded extension of finite dimensional algebras. And then algebra B belongs to the class H if and only if algebra A belongs to the class H2. And actually now we are going to study some similar problem for the world of pseudocompact algebras. And I will briefly recall some basic notion of pseudocompact algebras. I will explain how to define Hochschild homology for the world of pseudocompact algebras. And also we will study some analog of Hahn conjecture for the pseudocompact algebras. Actually, let me briefly recall what are pseudocompact algebra and give you also some important examples of the pseudocompact algebras. So, a pseudocompact K algebra is an inverse limit of finite dimensional K algebras. So A equals inverse limit AI, in which each AI is finite dimensional K algebra. In particular, any finite dimensional K algebra is a pseudocompact algebra. And also another way to think about pseudocompact algebras, it is pro-object in the category of finite dimensional K algebras. Okay, examples include the following one. So actually a power series ring in one variable, it is a pseudocompact algebra because it can realize this algebra as an inverse limit of the following finite dimensional algebras, k of x over x into the power n. Okay, one more example. If G is a profinite group, in this case we can consider what is called completed group algebra of a profinite group. It is defined as an inverse limit of ordinary group algebras G over U, in which U runs over all open normal subgroups in G. And actually these guys, they are finite dimensional K algebras, and actually this is why this algebra it will be pseudocompact K algebra. Okay, one more important example, given any Q over Q, it can be finite or it can be infinite. In this case, we can consider what is called completed path algebra of this any Q over Q. It is nothing else as a completed tensor algebra given by the semi-simple pseudocompact algebra given by the vertices of this Q over Q, and also sigma pi modulo given by the Arab spaces in the Q over Q. And actually important difference between ordinary path algebra and also completed path algebra is that we are allowing the path of infinite lengths in Q. Another important source for the pseudocompact algebras is given by the K coalgebras. So, given any K coalgebra C, we have the following. Applying the fundamental theorem for coalgebras, we have that C can be written as direct limit of Ci, in which all Ci are finite dimensional subcoalgebras in C. Okay, and now we can consider the following. And we can take the dual space of C. So actually dual space of C, it is given as hom over k C into the k. It is nothing else applying the fundamental theorem for coalgebras as hom over k, inductive limit of Ci into the k. And now we can interchange the order between hom and v. And actually we will get the following. It is going to be inverse limit of hom over k Ci into the k. Then it is going to be inverse limit Ci star. And actually now we have the following. As each Ci are finite dimensional K coalgebras, its dual space is going to be finite dimensional K algebra. So actually each Ci star, it is finite dimensional K algebra. and hence C star it is pseudo-compact K algebra. Okay, and hence taking any K coalgebra C, its dual space C star is a K pseudo-compact algebra, and in this way we get an important duality between the category of K coalgebras and also the category of K pseudo-compact algebras. So actually to now studying models over pseudo-compact algebra to what is well behaved are somehow the models that calls pseudo-compact models. Okay, so actually a model M is called pseudo-compact model if I can write M as inverse limit of Mi, in which all Mi are finite dimensional models. In this case, the category of pseudo-compact A models is an abelian category with enough projectives. And hence it makes sense to somehow to talk about what is projective dimension and what is global dimension and so on. In particular, let me give you one example. And actually let us take a commutative pseudo-compact algebra R, a commutative pseudo-compact algebra R. In this case, global dimension of the power series ring R of x is going to be as you expected. It's going to be global dimension of R plus 1. Okay, it also makes sense to talk about a Hochschild homology in this context. And the definition precisely the same as Cartan-Eilenberg did for ordinary case. So actually Hn of A is given as a tor. But actually slight difference is the following one. So in our case the tor should be a derived functor of a completed tensor product. A completed tensor product it is given by the universal property between pseudo-compact models such that a completed tensor product is again pseudo-compact model which satisfies some universal standard properties. And also enveloping algebra AE is going to be A completed tensor product over K, A opposite. In this case, enveloping algebra is going to be new pseudo-compact algebra which encodes pseudo-compact A by modules. Yet something the same which do ordinary enveloping algebra, but actually instead of taking all the modules, you are taking pseudo-compact modules. And actually this is why you should change into the completed tensor product. Okay, as long as we have a well-defined notion of the global dimension and also Hochschild homology for pseudo-compact algebras, we can ask whether or not some question of Hahn conjecture can hold in this context. It turns out that the word by word precisely the same statement, that is, global dimension is finite if and only if the Hochschild homologies vanish for large enough degrees n, is already wrong in some simple cases. Okay, for instance, and actually let us take infinite quiver, the finite line quiver. And actually we can consider as following pseudo-compact algebra. It's going to be completed path algebra of this quiver, modulo radical square of this algebra. it is nothing else as an inverse limit of the following finite dimensional algebras. It's gonna be ordinary path algebra of this finite quiver 1, 2, 3 until n modulo radical square. And it is actually a relatively easy exercise to check that the Hochschild homology of this algebra it is concentrated in degree 0. But on the other hand, as we saw, global dimension of this algebra is going to be exactly n-1, and actually this is why global dimension here increases, and actually this is why morally global dimension of A is going to be infinite. Okay, what we're going to do is the following. We say that the pseudo-compact algebra is p-regular if we have the following. If we have that the projective dimension of any pseudo-compact A model is finite. And actually, let me give you a very simple remark. In the case when we have our pseudo-compact algebra is already finite dimensional, in this case, a p-regular is exactly the same as global dimension of I is finite. And also other remark, if we have finite global dimension in A, is it is obviously that A it should be p-regular in this case. Okay, so and actually one can study the following question, which is going to be analog of Hahn conjecture for the world of pseudo-compact algebras. So and actually the question is whether or not for all the pseudo-compact algebras we have the following. A is going to be p-regular if and only if the Hochschild homology of A vanishes for large enough degrees n. And now let me introduce the class H hat, the class of pseudo-compact algebras A, such that condition star holds. And actually what I'm going to show now is that actually this class is stable under certain extensions of pseudo-compact algebras. Let us okay, and now let B sub A be an extension of pseudo-compact algebras, and we say that it splits if you have the following. If I can write A as B plus some B by model M, and we say that it is P bounded if we have the following. The projective dimension of M as B by model is finite. Also M is left or right B model. Also condition 3, a tensor power of M is projective for some n, and also we have the following, and also a technical condition, A has a finite BR relative projective dimension. And actually now let me give you some remark. For finite dimensional objects, the split bounded extensions in the sense of Sibyl's, Marcos, Lancelota and Solitar, it implies that actually this extension going to be split P bounded in our sense. And actually this is why this condition is already generalized, the conditions of bounded already in finite dimensional cases. Okay, so and now the principal theorem is a joint result with John Macquarie, and it says the following. So let A equals B plus M be split P bounded extension, and then B belongs to the class H hat if and only if A belongs to the class H hat. And hence class H hat it is closed under P bounded extensions. And the proof of this theorem is based on the existence of Jacobi-Zariski sequences in this context, which allows to control Hochschild homology of B and Hochschild homology of A. Okay, I could give some example of split p-bounded extension for pseudocompact algebras. And this example is inspired by the very similar example from the work CMLS. Okay, so and let B equals to completed path algebra modulo admissible ideal in which Q can be finite or can be infinite Q. And also let F to be as a set of new R's to which we're gonna add there to the quiver Q. In this case, we can consider the following pseudocompact algebra AF, which is given as a completed tensor algebra over pseudocompact algebra B, and also B by model NF, in which B by model NF is given as follows. Okay, algebra AF writes as B plus B by model T, in which this B by model T it is nothing else as a product of completed tensor powers of the model NF. As long as model NF it is already projective as B by model, we have that this model is also projective as B by model 2. And hence the conditions 1, 2, 3 are already satisfied. The condition 4 also holds true in this case, it is not hard to check, and hence we get a split p-bounded extension in this case. Okay, and actually, as I said before, split bounded extensions implies it is going to be also split p-bounded extension. And actually now let me give you one example of split p-bounded extension which is not split bounded extension. Okay, and actually let us take the following quiver Q. It has 4 vertices. It has 3 arrows here, and also it has 1 loop at vertex 2. And actually now let us take algebra B. It's going to be pseudocompact algebra given by the completed path algebra of this quiver. Also M prime is going to be B by model, which is given as follows. S3 completed tensor product S1, in which S3 is simple model at vertex 3. S1 is a simple model at vertex 1, and also we have a projective B by model at vertex 2. It's going to be B, idempotent at vertex 2, completed tensor product E2B. Okay, and actually let us take the following pseudocompact algebra. It's going to be completed tensor algebra T B M prime, and actually this algebra is given as follows. It's going to be B. It's going to be B product M prime into the completed tensor power 2 product blah 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 until M prime into the completed tensor product n until so on. And actually now there is infinite product that we will call S model n. In this case, we have the following. So A is going to be B plus this model. There is actually B by model n. Okay, and actually we claim the following, that this extension A equals B plus m is split p-bounded extension, to which is already some work to check that this extension is p-bounded, which is not bounded because this B by model m is not tensor nilpotent. Okay, thank you very much for your attention. This was all that I have prepared for this talk. I will be very happy to answer any questions you might have. And finally, the most important information, happy birthday, dear Said.